Sweet, good afternoon, y'all. I'll give a second for folks to trickle in, and then we're gonna get to moving. We do have a fair amount of things to cover today. So let me get some fresh paper over here. Fire up yonder.cam.
Professor, I had a quick question.
Sure.
On the test, are we gonna have formula sheets?
No.
Like for the volume of a sphere, surface area of formulas, all that
I'm
stuff?
afraid not, no. If there is a formula that I require of you on the exam that is not a known, well, sorry what it says. Simple formulas from geometry you should know, right? Like the area of a circle or the volume of a sphere. Volume of a sphere, maybe I would give to you on the test, but certainly no formula sheets. If the test calls for an esoteric formula, I don't know, like the surface area of a tetrahedron or something, then I might give you that formula on the test. Because certainly I'm not here to test your ability to memorize old formulas from geometry, but definitely no formula sheets. No.
Got it.
So today, I want to do a few things. Last night, I pre-recorded lectures for the rest of the week. That means today I need to kind of close the gaps between the things that we had done last Friday and the things that I have already recorded for you in this week's lecture. And I split the material up a little bit because I wanted to cover kind of the tougher topics in person with you here today so you could ask questions. So I'm going to flip over to the syllabus for a minute so that I can show you how we're going to split things up. So last week we talked a little bit about linear approximation. Today we're going to talk a little more about that, but it's going to go quite quickly. The lectures that I recorded for you cover the min-max problems and a little bit of the graphs of f and f prime, which leaves L'Hopital's rule, curve sketching, and linear approximation. So I'm going to start with the linear approximation. That's what we introduced last week. But then I'm going to jump around a little bit through these chapter 4 concepts, probably leaving L'Hopital's rule out, if anything, today. So this is MAC2311, section 004. Today is the 19th. And today we're going to talk about linear approximation, and differentials. We're going to talk about graphs of f and f primed. And maybe a little bit of curve sketching. All right. So exam is on 10/23. No, 10/23, that would be this week, would it not? That would be this Friday. So I'm thinking, what did we say last time? That this week we would cover up through section 4.5, and then next Monday we will cover section 4.7, and that's when I'll release the study guide. So your exam is a week from next Monday. Your exam is going to be on November 2nd. So yeah, if you're keeping track, exam 2, the tentative date is 11/2. I might move that around, but probably not. Probably that's where it's going to stay. All right. So the linear approximation and differential stuff, we've talked about that before. We actually did a really nice example. last Friday. And I invite you, if you don't remember that, to please go back and rewatch the end of the video last Friday when we talked about linear approximation. Today I'm going to do one more example, and then I'm going to show you the notation for differentials, but we're not going to use differentials to do any approximating because the notation there is really poor. There's one reason to talk about differentials in Calc 1, and that's because we'll need them when we talk about substitutions. But the basic idea behind the linear approximation is that if you have some point a comma f of a on your graph, and f of a is not terribly hard to compute, but you want the value, the y value on your graph at some nearby point. So here would be x, and you're looking for this y value f of x. So maybe last time the example we had was a square root, right? You wanted to figure out the square root of 2, and that's kind of tricky, but the square root of 9/4 is very easy. And the trick is to think about the tangent line. So if I make the tangent line to f of x at x equals a, that is the best linear function for approximating f of x nearby a. So in other words, if this function here is the linearization, L of x is very, very close to f of x as long as x is close to a. And L of x, remember, is just the tangent line. So the error is this vertical gap between the pink dot and the dark dot. Because the tangent line has the right slope, it's kind of like the slope of the curve at that point, it is the best line for approximating f of x near the point a comma f of a. So if I'm having a hard time finding the y value here, I can find the y value here instead and be reasonably confident that the pink y value is very, very close to the dark red y value. Now here, L of x, there's two ways to remember this. It's the tangent line to f of x at x equals a, just solved for y. Or if you want to remember a formula, it is f of a plus f primed of a times x minus a. I'm not big on memorization. I like to memorize as little as possible and understand as much as possible. So for me, rather than memorizing this formula, I would just remember that L of x is the tangent line to f of x at a solved for y. But I know a lot of people do like to remember formulas, so that's the formula. And the idea is that plugging x values into this thing is very simple because it's a linear function. So let's do it. Let's approximate something using the linearization. I'm going to go to, there's this, derivatives, intermediate forms of Vitale's rule, optimization, graphing, calculus, line derivatives. Oh, it's buried in here, isn't it? Yeah. Linear approximations. Okay. Application of physics is all good stuff. I won't want to spoil it for you. Find the linearization, but I think much better. Yeah, let's So I say we want to find, I'm looking at number 5 here, find the linear approximation to the function f of x equals the square root of 1 minus x taken at a equals 0, and then use it to approximate these numbers. And they want us to draw the corresponding picture like I had over there. So let's do it. This would be an exam level problem. Use the linearization of f of x equals square root 1 minus x at a equals 0 to approximate the square root of 0.9. I'll just do the 1. And we'll say draw the picture. So I'll actually start by drawing the picture. Does anybody know what the graph of this function looks like without cheating, without putting it in Desmos? This is a skill that we should remember from pre-calculus. We can graph this as a transformation. The square root of 1 minus x is the square root of negative x minus 1. So this is the square root function shifted to the right 1 and also reflected horizontally. So you do the horizontal reflection first and then the right shift. So the graph of this function looks like 1 over here. Regular square root looks like this. So the horizontally reflected square root looks like this. So the horizontally reflected and then shifted square root looks like this. Now we want, so this is our a value. We want to approximate the square root of 0.9, which would be the y value on the graph of that function right there. And the way we're going to do it is by first building the tangent line or the linearization to this function here at a equals 0, because that's what they told us to do. And then instead of finding the exact y value here, we will find the y value here, which from the picture you can see is very, very close to the thing I want. All right. Any questions about what we're doing here or what this picture represents in the context of the problem?
Is that 0.4 or 0.9?
0.9. Sorry. Okay, so we're going to build the linearization. To do that, I need the derivative. The derivative of square root 1 minus x, that's d dx of 1 minus x to the 1/2 power. We need the chain rule there. That's 1/2 times 1 minus x to the negative 1/2. And then by the chain rule, I have to multiply by the derivative of the inside. The derivative of 1 minus x is just negative 1. So the slope of my tangent line is f primed of 0 is 1/2 times 1 minus 0 to the negative 1/2 times negative 1. 1 minus 0 to the negative 1/2, that piece, that's 1 over the square root of 1. And then, of course, I have this negative 1 here. So the square root of 1 is 1. So this is 1/2 times 1 over 1 times negative 1, which altogether is negative 1/2. And the point on the graph there at x equals 0, f of x equals f of 0, which is the square root of 1 minus 0, which is 1. So my linearization the pink line up there is f of a, f of 0, which is 1, plus f primed of 0, negative 1/2 times x minus a, and a again is 0. So in other words, this is 1 minus 1/2 x. So if I want to know the square root of a number, I figure out what I would plug in here to get the square root of that number. So if I want the square root of 0.9, I'm plugging in what for x here? That's the square root of 1 minus 0.1, right? In other words, this is f of 0.1. And f of 0.1 should be very close to L of 0.1, because f of x is very close to L of x as long as you stay reasonably close to a. L of 0.1 is exactly 1 minus 1/2 times 0.1, which is 1 minus 1/20th, because 0.1 is 1/10. 1/2 times 1/10 is 1/20th. And this is 19/20ths. So the square root of 0.9 is pretty close to 19 over 20. We can check how close. I don't think this will be quite as good as the example that I made up for you guys the other day. Because here, a is 0, and my point where I'm actually using the linearization is 0.9. That's kind of far away from 0. But still, let's get a feel. So the square root of 0.9 is 0.948, blah, blah, blah. And 19 over 20 is 0.95. It's not bad. The first decimal is correct. And the second decimal, if you rounded the true value to 2 decimals, it would be this. So it's a pretty good approximation. So again, any questions on what we did here, how we did it, why we did it, or how it ties into the picture?
Why did you plug in 0.1?
So my goal was to approximate the square root of 0.9, right? And the function I'm working with is the square root of 1 minus x. So I have to figure out what x value do I plug into this to get the square root of 0.9. In other words, I'm not just working with the function square root x. They told me to work with the function square root 1 minus x. So the way to get this function to output the square root of 0.9 isn't to plug in 0.9, it's to plug in 0.1. Because 0.9 is 1 minus 0.1. All right, if you look down here, the square root of 0.9 is the square root of 1 minus 0.1. And my function f of x is the square root of 1 minus x. So I had to figure out f of what gives the square root of 0.9. And the answer is x equals 0.1. Does that make sense? I didn't hear a yes or a no there. Are we clear on why we're plugging in 0.1?
Yeah.
Okay, cool. Alrighty then. So I don't feel compelled to do more examples of the linear approximation stuff. It's really not anything amazing in terms of like what you're doing. You're just calculating the tangent line, and then you plug in a particular x value. What is neat here though is the picture, right? And trying to understand how the picture relates to the problem. The idea that the tangent line stays as close as it possibly can to the graph of the original function. There is no other line that does better. And in differential geometry, which is the mathematics behind general relativity and a lot of other things, understanding the derivative as the best linear approximation is actually a very big deal. The other thing I do want to talk about from this section is differentials. And we're not going to talk about them much. I don't like the way this section handles them, because again, as someone who appreciates differential geometry, the notation they use here is really bad. And be good. Stop. No him. Stop it. Sorry, my dog. All right. This is something that we're
Mister,
going to use.
I'm assuming like Newton's laws, they're basically approximations of like general relativity and stuff, right?
Sort of.
Or not really?
Newton's, if you apply general relativity under some really incorrect assumptions, you get Newton's laws. But the whole point is that general relativity extends Newton's laws substantially. We can talk about that at a different time, but for now, differentials. So we've seen that if y is f of x, then just notation dy dx is f primed of x, right? On the left, you have the Leibniz notation, and on the right, you have the prime notation. It turns out that with the right kind of formalism, you can treat dy and dx as things in their own right. You can think about dy as the infinitesimal change in y, and dx as the infinitesimal change in x. And that way dy dx, written that way, looking like a fraction, really is like a slope. It's the rise over the run. It's just a very small rise over a very small run. These are called differential forms. These are called one forms. So this is the differential form of the derivative. And if I want to write dy on its own, I can treat dx as a variable and say, okay, I'm gonna multiply by dx. I use quote bunnies there because they don't represent real numbers. They represent infinitesimals, which are not real numbers. But the arithmetic still works. And you see that dy is f primed of x times dx. This is the differential of y. That's how we say it. And it turns out to have some very specific meaning in geometry. This is called a one form. And you can think of it as a certain kind of function, a function from a vector space to the real numbers that tells you how much f of x is growing in a neighborhood of a certain point. But for us, it's just a matter of notation. So if I say calculate the differential dy, then you would find the derivative, and then slap on a dx. So for example, if y is cosine of e to the x, then dy, I would calculate by first calculating the derivative here. Derivative of cosine of e to the x, we use the chain rule. That would be negative sine of e to the x times the derivative of the inside, which is e to the x, and then you would slap on a dx. Or if u was equal to x squared plus 1, then du, I differentiate this thing. The derivative of x squared plus 1 is 2x. So I would have 2x dx. Or finally, I could say something like if z is equal to x times the natural log of x, then dz would be, I need to differentiate this, which requires the product rule. If I differentiate the x, I get 1. So it'll be 1 times ln x plus x times 1 over x. That's using the product rule there. And all of this in parentheses would get multiplied by dx. So these are differentials. They're in the textbook, if you read the section, and you're welcome to do so, it's the same as the linear approximation section. They then talk about treating this as delta y, it's like a measurable actual change in y, and this as delta x, a measurable actual change in x. And you're able to get out the linearization formula, but it involves this really bad abuse of notation. Right, so dx is technically not a number. Dx is a differential one form. If you want to be technically correct about it, dx is called a one form. You can Google here, I'll show you just real quick. Differential form. This is kind of the fundamental object of study in differential geometry. So again, very intimately related to general relativity. But all of this is way over our heads. So what we're talking about here are the simplest types of one forms. One forms for us are really just derivatives. So yeah, treat it as a variable. Treat dx as a variable. Treat dy as a variable. Not d and x separately, but just dx as a variable and dy as a variable. You can manipulate them as such. The easiest way to understand them that is not blatantly wrong is to say that they're infinitesimals. So infinitesimals are smaller than any real numbers, but they're still not zero. So there's this set called the hyperreal numbers or the surreal numbers that is somewhere between, you know, all the real numbers and zero. You have these very, very small things called infinitesimals. And they follow essentially the same arithmetic that real numbers do and the same algebra that real numbers do. So you can treat dy and dx as infinitesimals, or in your head, just think very, very small number. And then you can do algebra and arithmetic with them as well. But for our purposes, the thing is that later when we're doing integrals with substitutions, we're going to need to calculate differentials like this to plug in. So you just need to know the notation. That's the main thing, is that right now you need to know, oh, if y is e to the x or cos e to the x, then dy is negative sine e to the x times e to the x dx. So yeah, treat dy and dx as variables or du and dx as variables, and don't panic too much about what they mean. If you want, you can think of them as infinitesimal changes in x and y. And if you're feeling very fancy, you can pick up a differential geometry book and start trying to understand them from the true big boy perspective, which is as differential forms, one forms. So that's all I have to say on differentials. Nothing magical or special there for us yet, although they will come back later. The next major topic I want to cover with you guys today is coming from chapter 4, I think probably 4.2, and it discusses the relationship between the graph of f and f prime. And this should all be familiar from section 2.8, where I gave you the graph of f and had you sketch the graph of f prime by guessing at slopes of tangent lines. Here, though, we're going to start inferring explicitly things about the graph of f from the graph of f prime. So I have a few theorems for you, and I want to make sure I don't skip over anything, so I'm going to back here just for a second. Value theorem, derivatives affect the shape of the graph. Yeah. Right. Okay. Yep, and we're going to pick this up on Monday. I actually have, sorry, not Monday, on Wednesday. I have a little bit this information in there, but here's the main thing. So increasing and decreasing. Theorem. If f of x is differentiable on the open interval AB, and f prime of x is positive on AB, then f itself is increasing on AB. And if f primed of x is negative on AB, then f of x is decreasing on AB. So this is a big deal, and we've illustrated and discussed this a number of times in the past. So let's say we've got a function looking like this. I'll call this 1, 3, and 5. I always get calls at the most inopportune times. So this is the graph of f of x. I think we would all agree, based on our experience in pre-calc and elsewhere, that the function is increasing here, decreasing here, increasing here, and decreasing here. And if you look at tangent lines anywhere over here, they will all have positive slope. If you look at tangent lines over here, they all have negative slope. So f is increasing on the intervals -∞ to 1, 3 to 5. And that corresponds with the fact that f primed is positive on the intervals -∞ to 1 union with 3 to 5. So everywhere I'm increasing here, if you look at these tangent lines, they all have positive slopes. Everywhere I'm increasing here, look at these tangent lines, they all have positive slopes. And f of x is decreasing on, well, from 1 to 3, unioned with 5 to infinity. And it's definitely the case that f primed of x is negative on interval 1 to 3 and 5 to infinity. So if I ask you to discover where a function is increasing, remember, this is always given as open intervals of x values. Where is something happening? That always means for what input or for what x value. Never give me ordered pairs, never give me y values. I don't want those. That's not the right way to think about it. The reason the definition of a function is what it is so I can describe what's going on just in terms of the inputs. If I ask you where is a function increasing, I'm asking for what x values is the function increasing. You should take the derivative and set it greater than 0. Solve that inequality. That will be your answer. If I ask you where is the function decreasing, same thing. Take the derivative, set it less than 0. Solve that inequality. That will be your answer. And in general, we want to get to a place where we can figure out both of those things kind of at once. Figure out where a function is increasing, where a function is decreasing. I'm going to do an example, but before I do that, I want to talk about one other thing, and that's concavity. So in addition to increasing and decreasing, there are these notions of concave up and concave down. First, the theorem. If f is twice differentiable, on the open interval a to b, then f double primed being positive on AB means f of x is concave up on the interval a to b. And if f double primed of x is negative on AB, that means f of x is concave down on AB. And I'm going to draw pictures and try to explain to you guys what this concave stuff means. The easiest way to think of it is concave up would hold water, and concave down, water would run off the back. But really, you should think about it in terms of rates of change if you want to try and understand it. So suppose I give you a function looking like this. Certainly it's increasing. But if you look at the slopes of the tangent lines, here, f primed is really big. Right? The slope of this tangent line is really, really large. Here, f primed is still positive, but it's not as big. Here, f primed still positive, but not as big. Here, again, f prime positive, but getting smaller. So if this is the graph of f, the graph of f primed starts out, okay, positive and enormous, like way up here. Positive, but not quite as large. So like here. Positive, but getting closer to 0 here. And positive and almost 0 here. So what's going on? F is increasing, but F primed is decreasing. The function overall, the original function, is definitely increasing everywhere. You're going uphill as you go left to right. But the derivative, the rate of change, is going down. You're increasing really fast, increasing less fast, increasing less fast, increasing less fast. And that corresponds to the derivative having a shape something like this. So this would be your graph of F primed. The fact that this is concave down, right, kind of looking like a turned over bowl, corresponds with F primed decreasing. So the graph of F double primed here, the second derivative is everywhere negative, right? Here, F primed is decreasing, and it's decreasing really fast. So let's play the same game, but now between F primed and F double primed. F double prime, the slope of F prime starts off way negative. And then here, the slope is still negative, but not as negative. So we're getting a little bit gentler. Here, the slope of F primed is still negative, so F double primed is still negative. And here, the slope of F primed is gentling out. So here's a graph of F double primed. Increasing concave down means the first derivative is positive, but first derivative is decreasing. You're increasing, so your tangent lines are all positively sloped, but the tangent lines, while they stay positively sloped, are getting smaller, which means F primed is decreasing, which means F double primed is negative. Cool, right? So I'll give you a second to kind of draw these pictures and think a little bit for yourself. Make sure your notes are clear. F primed is the rate of change for F. F double prime describes what we call curvature. And in this one-dimensional case, where the inputs and outputs are both one-dimensional, real numbers, you know, we call that curvature concavity. So I'm going to kind of give you a table here with some little pictures in it. Yeah. So F is increasing, which means F primed is always positive. The graph of F primed is always above the x-axis. But the slope of F is going down, right? Here the slope is like 5. Here the slope is like 2. Here the slope is like 1. Here the slope is like 1/2. So if you plot those points, you get the graph of F primed. And F primed is decreasing because it's like 5, 2, 1, 1/2. 5, 2, 1, 1/2. So the shape of F, the fact that it's going up but has this like bowl shape, is coming from the fact that F primed is decreasing. Since F primed is decreasing, that means its derivative, which is F double primed, is negative. So the fact that F here is concave down is because F double primed is negative. F double prime being negative means F prime is decreasing. F prime decreasing means F's graph has this shape, concave down, because the tangent lines are going from steeper to less steep. It's cool shit. So I hope you see now why I said section 2.8 was so important. You need to be able to visualize the graphs of f and f prime. Not just to make this connection, but also to make this connection. And once you understand how this connects to this and how this connects to this, you can see right away how these two connect. If you want the physics analogy, if f is your position, then remember f primed is your velocity and f double primed is your acceleration. So this is like how hard your foot is pressing on the gas. This is how fast you're going, and this is where you are. If I have my foot on the gas really hard at the start, but then I start letting off the gas, I'm still certainly going forward. So F should still be increasing. But I'm letting off the gas, so I'm going forward less and less and less and less fast. Yes, just like the points on F primed are slopes on F, the points on F double primed are the slopes on F primed. The relationship there is the same. You differentiate once, that takes you from wherever you are to a graph made out of the slopes of the tangent lines of where you were. So if you differentiate again, that takes you from here to a graph made out of the slopes of his tangent lines. That's why I drew these in blue here. I hope you can see that. And down there in blue as well. So the slopes of these tangents are the y values here. If we were to keep differentiating, would the graphs repeat in a pattern if this wasn't in context of physics? Well, sort of, maybe, not necessarily.
I mean, I was saying on this case, since that looks like ln(x), then everything else would be like, power rule.
This does kind of
the
look like ln(x).
Derivatives. Yeah, like shifted.
And this does kind of look like a shifted 1 over x. There's some truth to what you're saying, but I see what she's asking there is that like this graph kind of looks like this graph. And do we always run in a cycle of 3s like that? That's not true. So the graph of f double prime doesn't necessarily need to look anything like the graph of f. It's just a coincidence that in this particular case it does. In the setting of physics, there is a neat interpretation for the higher derivatives: position, velocity, acceleration. And if you think about how fast your acceleration is changing, we call that jerk. Like something gets pushed really hard, then your rate of change is changing. Its rate of change is changing. And the rate of change is changing so fast, it feels jerky or bumpy. So we call the third derivative of position jerk. But the fact that this graph looks kind of similar in shape to this graph, that's not always true. The graph of f double prime does not necessarily always look like the graph of f.
Since we're talking about like concavity, if it were just to ask us, hey, what is the third prime of f of x? If we were to like assume a pattern, since the first one is concave down, then the next one should be up, the next one is down. Can we say the third one is concave up if we were to ask it like that?
That's a really good
Yes,
question.
but it's only for this type of function.
Yeah.
Yeah, but like the pattern of concavity, like
it does not necessarily work like that, no. So there are a lot of examples. Easiest examples here come from polynomials, right? So first, let me make clear what concavity is in terms of pictures. Look at those 4 cases, and then I'll address your question there through some examples. So combinations of increasing, decreasing, concave up, and concave down. So you can have all of the possible four combinations there. You can be increasing and concave up. And that looks like this. Right, here we are increasing and we're concave up. Our slopes of tangent lines are not only all positive, but they're getting steeper. So here, F primed is positive, that's the increasing, and F double primed is positive, that's the concave up. You can be decreasing and concave up. That looks like this, where F primed is negative, you're always decreasing. But if you look at the slopes of the tangent lines, this is really negative. This is less negative. This is less negative. This is less negative. So the second derivative is positive. So here F primed is negative because we're decreasing. But if you think about how the slopes of the tangent lines are changing, this is very negative, less negative, less negative, less negative. So those slopes of tangent lines are getting larger, right? They're getting less negative, which means that F primed is increasing, or F double primed is positive. You can be increasing and concave down. And this is like the picture we had over there. The natural log is a good example, but it's not the only one. Anything whose graph, or a portion of whose graph looks like this, is increasing and concave down. Increasing here, so F primed is positive, and you can see that the slopes of all these tangent lines would definitely be positive, but concave down, because the slopes of the tangent line here is very steep, maybe slope 5, slope 3, slope 2, slope 1. So these slopes are getting smaller, which means that the derivative of the derivative, F double primed, is negative. And then the last possibility is you can be decreasing and concave, what did I do? Increasing, concave up, increasing, concave down, decreasing, concave up. So we still need decreasing, concave down. Hamlet, do not eat that cat food, buddy. You are going to be in trouble. So if you are decreasing and concave down, then you look something like this. So decreasing, all of the tangent lines here definitely have a negative slope, but also they're getting more negative. So F primed, the slopes are themselves also decreasing. So you're decreasing, so F primed is negative, and then concave down, F primed is also negative. So these are the four kind of possible graph shapes. One of
Okay,
the
thank you.
sections here is curve sketching. And the best way to get good at drawing really good graphs is by figuring out where your function is increasing, decreasing, where your function is concave up, concave down, and to then use that information to connect some dots with appropriate shaped curve pieces. Now, we wanted to look at an example. Let's do it. Let's find a nice concrete example. Oh yeah, we should define inflection points. Second derivative test I talk about in the video for Wednesday, so I will leave that off for now. But let's sketch a graph here. Let's find where f of x equal x to the 4 minus 4x cubed is increasing, decreasing, and concave up, concave down. And then I'll try to connect this in with some of the stuff that you will be learning on Wednesday. So if I want to know where this function is increasing and decreasing, I should take the derivative and then figure out where that function is positive and negative. The derivative here is easy. That's 4x cubed minus 12x squared. This is a 3. I can factor out a 4x squared, and what would be left then is x minus 3. So remember, I'm trying to figure out where f primed is positive and negative. I'm trying to like solve the inequality f primed is greater than 0. You may or may not remember from your pre-calculus class, the way to do that, solve a nonlinear inequality, is to find all the places where the object is capable of changing sign. That's anywhere the object is undefined or goes through the x-axis. Since this is a polynomial, it's never undefined, but it's capable of changing sign at its two x-intercepts, which are 0 and 3. You'll see on Wednesday, these numbers are called critical numbers. To the left of 0, I could plug in x equals 1, or sorry, negative 1, say. Here I would have 4 times negative 1 squared, that's 4, times negative 1 minus 3, that's negative 4, that would be negative 16. So over here, I calculated f primed of negative 1 as negative 16. In particular, f primed is negative there, which tells me f will be decreasing there. Between 0 and 3, I could test x equals 1. When I plug in 1 here, I get 4 times 1 minus 3. That's 4 times negative 2, or negative 8. F primed of 1 is negative 8. So f primed is negative between 0 and 3 as well. And then to the right of 3, I could plug in like x equals 4. And I would get 4 times 4 squared, or 4 cubed, which is 64, times 4 minus 1, which is 1. So f primed of 4 is positive 64. This is positive. So from this, I can conclude that f is increasing on the interval 3 to infinity and decreasing on negative infinity to 0, union with 0 to 3, always open intervals. So something funny is happening at 0. We're like decreasing, 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 and then decreasing, decreasing, decreasing. There's a horizontal tangent line here and here. One of these is a local min. The other one is not. Yeah, so the fast way to do what I just did is using multiplicities. So you test 1 point, like you test negative 1 over here, and then you recognize that the root at 0 is multiplicity 2, so you won't change sign when you hop over 0, you'll stay negative. The root at 3 is multiplicity 1, so you will change sign as you hop over 3. That is definitely how I do this stuff when I need to do it. And if you remember how to solve these inequalities quickly using the multiplicity trick, I absolutely recommend you do that much, much faster. You can even use end behavior, and that'll get you out of having to even test points at all. End behavior and the multiplicity trick. That's how I teach it in pre-calc, but I know not everybody gets that, so I'm trying to teach it here in a way that I trust everybody can handle. F double prime is what I need for concavity. So I differentiate again, and it's easier to differentiate from this form than from this form, because here I don't need the product rule. Here I would. 4x cubed, his derivative is 12x squared minus 12x squared, his derivative is 24x. And this can be factored as 12x times x minus 2. And I do the same thing. I build a number line for f double primed. I have 0 and 2 to play with now because this is 0 at 0, this is 0 at 2. Yeah, multiplicity is for sure the good way. So let's try that. I know the end behavior for 12x squared minus 24x is up on both sides. So over here, this thing has to be positive. The root at 0 is of multiplicity 1, so we got to change sign. And the root at 2 is of multiplicity 1, so I got to change sign again. No test points. That's the fast way. So I'll be concave up f of x. Therefore, f of x is concave up on negative infinity to 0 and 2 to infinity. And f of x is concave down on the interval 0 to 2. All right, so we found where f is increasing, decreasing. We found where f is concave up and concave down. The last and fun thing to do here is to sketch a graph. And that's really what you're going to be doing in 4.5. Since we're so close, we might as well go ahead and sketch a graph. I just want to point something out, a definition, but maybe first let's draw the graph. So you can put these two number lines together into one number line. The shape of f as increasing, decreasing, concave up, and concave down. So I put all the numbers that were on any of these number lines here. Everywhere to the left of 0, f primed was negative, so I was decreasing, and f double primed was positive. So over here, f of x is decreasing and concave up. Between 0 and 2, well, f primed is negative everywhere from 0 to 3. So definitely from 0 to 2, we were decreasing. And f double primed is negative, so we were concave down. Between 2 and 3, f primed still negative, so still decreasing. But everywhere to the right of 2, f double primed is positive, so we're concave up. And then everywhere to the right of 3, f prime is positive, so we're increasing. And f double prime still positive, so we're still concave up. So the shape here is decreasing concave up. That's like this. The shape here is decreasing concave down. That's like this. The shape here is decreasing concave up, which is like this. And the shape here is increasing concave up, which is like this. And if you think about stitching pieces of graphs together that have these shapes, you see that right here at 3, I had to have a local min because I go from decreasing to increasing. Here at 0, something else happened. This is called an inflection point because you go from concave up to concave down. We also have an inflection point at 2 because we go from concave down to concave up. The last thing you need to draw a really nice graph of f, so I'll label this here. This is a min. And these guys are inflection points. An inflection point is a place where concavity changes. You go from concave down to concave up, or vice versa. All right, the last thing I need to draw a nice graph of f, and I'm going to go ahead and do this, is a point or two. So I know the y-intercept here is 0. F of 0 is 0. I know the end behavior is up on both sides because this is an even degree polynomial and the lead coefficient is positive. So I know I'm going to be going up on the left. Let me mark in the interesting things: 0, call this 2, call this 3. We know we go through the point 0, 0. We know our end behavior over here is up. We know our end behavior over here is up. And now I will use this stuff. So I'm decreasing concave up until I get to 0. At 0, I switch from concave up to concave down. So here's decreasing concave up. Here's decreasing concave down. So on the left, I can connect this with something that looks like that. At 2, I have another inflection point. I stay decreasing, but I switch back to going concave up. I don't know what f of 2 is, but I know I go from being concave down on the left, so I'm going to arrive something like this, to concave up on the right. So I'm going to do something here like that. And then at 3, I know I go from decreasing to increasing, and I'm concave up on both sides. So a reasonable graph would be something like this. All right. Now we'll come back and talk a lot more about these. Here I actually had a horizontal tangent at my inflection point. Here I didn't. So it could have been a smoother transition, something more like this. But that's the rough shape of this graph. And if you use this together with the information about the actual y value here at this min, the actual y value here at this IP, here we knew the y value, you take a couple points and you label everything, you graph those points accurately, and you connect them with the appropriate shaped pieces, you will get a damn fine graph. Yeah, and you can compare this to what they got. Right, here's their beautiful computer drawn graph. Here's our less beautiful graph. Notice I only ever plugged in one number, 0. So I wasn't even trying to guess at these y values. I was just trying to give us the right shape. But the shape is correct and it corresponds with what they have here. All right, one last little thing. We talked about the definition of an inflection point. We haven't looked at any cusps yet. I would like to look at an example from trigonometry. So sin x plus cos x. Well, no, we don't really have time, do we? Let me sketch for you a quick example here. So these people call me at just the worst times. All right. Here's the sine function graphed from 0 to 2 pi. Notice we're increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. Here I have a local max. Here I have an inflection point. Here I have a local min. F primed is cos x this is pi over 2, this is pi, this is 3 pi over 2, and this over here is 2 pi. In the graph of cosine, we know looks like this. Again, pi over 2, pi, 3 pi over 2, 2 pi. So the places where f primed go from positive to negative are places where f goes from increasing to decreasing. Here I have a local max, and f primed went from positive to negative. F went from increasing to decreasing. Here I have an inflection point, right, on the original, on f. And that is a place where f double primed has a horizontal tangent. Sorry, where f primed has a horizontal tangent. So a place where f double primed is equal to 0 and changes sign. Over here, I have a min on the graph of f, and f primed went from negative to positive. And up here again, I would have another inflection point on the original, where I go from concave up to concave down, because f primed is going from increasing to decreasing. So starting to connect the graphs of f, f primed, and I'll go ahead and draw f double primed down here. F double primed is negative sine x. Pi over 2, pi, 3 pi over 2, 2 pi. So again, you see inflection point on the original, horizontal tangent on the derivative, place where the second derivative changes sign. Local max on the original, x-intercept, or a place where f prime changes sign. Min on the original, place where f prime changes sign. Inflection point on the original, again, a place where f double prime changes sign, or a place where f prime has a local max. So starting to connect these pictures to each other, very important for where we're going. The inflection points on the original correspond to roots of the second derivative. Maxes and mins on the original correspond to x-intercepts of the derivative, and not just any x-intercepts, but x-intercepts where you change sign. And this is where we're going to pick it up on Wednesday, talking about mins and maxes. I'll give you the strict definition of a min and a max, the first and second derivative tests, and you'll go on from there. The other bit of the homework this week is going to have to do with L'Hopital's rule and a little bit more of the curve sketching. The curve sketching is the same stuff that we just did, right? Where we drew the graph of that polynomial based on concavity and inflection points, but there are some details. L'Hopital's rule, I loathe this section, but we do need to talk about it. It's something that people end up trying to use all sorts of places they shouldn't. But after that, the only thing we need to talk about is applied optimization. No, Caroline, at the start of class, we talked about this. So the exam, we will be ready for the exam by Monday. And so the exam will be the following Monday. I will release the study guide for exam 2 next Monday, and then exam 2 will be on the 2nd of November. All right. So yeah, we are, and we could do the exam sooner if you guys want. So it seems like you guys are a little bit anxious. Next Monday is when we will have all the material ready for the test. And we could do the exam like on the 30th or even on the 28th if you guys want. I'm going to be out of town for the remainder of this week. So I've pre-recorded your lectures. Yeah, I didn't think anybody was super anxious for that. So I'll release the study guide next Monday, which means the exam will be 11/2. Yeah, I imagine that's the case for everybody. It's going to put us a little bit behind in our schedule, but that's going to be just fine. Don't stress about it. So make sure that you're learning this stuff well. This is the very core of Calc 1. When you get to Calc 2, I will need you to have these skills and understanding in order to do well there. After exam 2, we're going to switch, stop talking about derivatives, start talking about integrals. Things are going to change quite a bit. So I really want you to invest the time, make sure you're very comfortable with the differentiation rules, especially the one that we've learned since exam 1, the chain rule. And then these applications. So next time you're going to learn about mins and maxes. And then after that, we're going to talk about curve sketching and L'Hopital's rule. After that, we're going to talk about applied optimization, and then you'll be ready for the test. So next Monday, a week from today, I will release the study guide. That's when we're going to begin the section on applied optimization. Next Wednesday, we'll probably talk a little more about applied optimization. And then next Friday, we'll have the review, and the following Monday will be the test. Alrighty, guys, that's all I got for you here today. I got to get running. I hope you have a lovely
We do have office hours today?
Yes, I do, although I will probably be cutting them a little bit short because I have to be getting ready to go out of town. But if there is something urgent, of course, feel free to come by the office hour.
All right.
All right, take care, guys.